distinguished guests, it is my pleasure to introduce NAE Executive Officer Al Romig.
Good morning, everyone. At this year's annual meeting, we are promoting engineering as a means to secure a more sustainable future, with a specific focus on measuring and communicating our progress. In today's plenary and forum, we will hear about some of the issues and challenges that we will encounter while striving to create a more sustainable society. The talks will provide a general coverage of sustainability and insights on life cycle analyses, artificial intelligence and sustainability, as well as the connection between sustainability and socio-techno-economics. First, we will begin with an overview. It gives me great pleasure to introduce a friend and former NAE counselor, Dr. Arun Majumdar. Arun is the Chester Naramore Dean of the Stanford Durr School of Sustainability, the J. Precor Professor of Mechanical Engineering and Energy Science and Engineering, and a Senior Fellow and the former Director of the Precor Institute for Energy. Formerly, Arun served in the Obama administration as the founding director of the Advanced Research Project Energy, ARPA-E, and as the acting Undersecretary of Energy. He also served as the Science Envoy for the U.S. Department of State and currently serves as the chair of the U.S. Secretary of Energy Advisory Board. Arun has been a friend and colleague within the NAE for many years. More of his biographical information is in your program. For the order of today's session, we will have 20 to 25 minutes for Arun's presentation and 15 minutes for questions. Our moderator, Deanne Bell, will join Arun on stage following his talk. Now please join me in welcoming Arun.
Thank you, Al. Good morning. Can you hear me at the back? Fantastic. Well, let me start by asking, anyone has their birthday today? Show of hands. Birthday, October 2nd. No one. Well, today happens to be the birthday of, I would say, an icon in sustainability, 154th birthday, Mahatma Gandhi. So, let me get my slides. I call this the defining challenge and opportunity of the 21st century. I want to put that in the context of some history. The first is that of human population. This is a chart. It took 1 million years for the human population to grow to 300 million. And in the last 100 years, that's the climb. It takes 13 years to add 1 billion people today. By 2050, 10 billion. By 2100, 11, plus minus. The uncertainty is 1 billion. Mostly in Africa. And you see a few dips around about a few hundred years back. Those are the pandemics. The Earth has never seen anything like this before. This is not an exponential. This is a super exponential. I call this the human tsunami. The Earth has never seen anything like this before. There are a few others. There's a human consumption tsunami. And I present that in terms of GDP. GDP, that's on production, and I call this the human consumption tsunami because people are producing because someone is consuming. And the outer curve is the per capita GDP. The inner curve is the total GDP, which is at about $100 trillion today. And it is also a super exponential. This has improved the quality of lives of human beings in the last 100 years, what our ancestor, my grandparents and great-grandparents, could not have imagined. To produce these things, and by the way, GDP is not a measure of human welfare, as was proposed by the proponent of GDP, Simon Kuznets, MIT. And yet we use that as a measure of success. I was deeply involved when I was in the Department of Energy to stop the BP oil spill, right in the trenches, working with the BP engineers. And if you step back for a moment, the BP oil spill actually increased the GDP because you have to deploy money, people have to clean up. But to produce these things, you need energy. And I'm putting these in arrows just to show my family. I was born in the 1960s. My two daughters were born in the 1990s, both engineers, by the way. My parents were born in the 1920s and 30s, and my grandparents at the turn of the century. And I put Sadi Carnot out there as well. And you can see that in 4 generations, we have turned from an agrarian society, the biomass is at the bottom, to 80% of our energy to produce those things and move us around coming from fossil energy. So it should not be a surprise that we have a global CO2 tsunami as well. Since it's early in the morning, especially for the West Coasters, here's a pop quiz for you. I'm going to throw you 5 numbers, and I want you to think about what they mean. There is no grading. I'll give you the answers. Talk about honor code. 1, 2, 840, 20. What do they mean? 1 is 1 degree Celsius. This is the global average temperature rise since the pre-industrial levels. It's 1.2, but let's call it 1. The next is 2. 2 degrees Celsius. This is the Paris Agreement, was tried to keep it below 1.5. 1.5 seems to be kind of baked in. Even IPCC is saying that now. So let's try to keep it below 2 degrees. You know, that's the goal, is to keep it below 2 degrees global average temperature rise. Global average temperature rise. The next number is 800. This is not 800 degrees Celsius. This is not Venus. If you are to keep the temperature rise below 2 degrees Celsius, we have 800 gigatons, billion tons of CO2 budget left. That's a lot of CO2. The fourth number is 40 gigatons of CO2 per year is today's emission rate. 40 gigatons of CO2. The last number should be obvious, 20 years. If you are to keep that constant emission, the emission's actually going up. We're talking about average temperature rise, but what really matters is this, is the distribution. This is some data from Jim Hansen's group at NASA. And these are summer temperatures. Some summers are hotter, some summers are cooler, red and blue respectively. So it's a nice Gaussian distribution. This is 70s, now going into 80s, and it's moving to the right. And it's not the average is certainly moving, but it's the tail of the distribution that creates havoc. That's a disproportionate effect, and that's what's going on. And so this is because of the CO2 and the temperature rise. You could do the same thing with water. This is water consumption. And water consumption, as you can see, has gone up exponentially, mostly for agriculture, and a lot of it for meat. This is the meat consumption going on in various parts of the world, and also the type of meat over the last 60 years. If you plot it over longer, it is an exponential rise. And meat has a disproportionate effect as well on the CO2 emissions, or the CO2 equivalent of methane, et cetera. For every kilogram of beef, there's 100 kilograms of CO2 equivalent emitted. And for pig and poultry, pork or poultry, it's roughly about 10 or so. So as you can see, these are all interrelated. I call this the defining challenge and opportunity of the 21st century, because what happens in energy affects water. What happens in water affects food. What happens in food affects biodiversity. That affects ecology. And that affects public health. And climate change adversely affects all of them. They cannot be separated. We all specialize. I focus on energy, but they're all interrelated. Now, the world has realized that this is an important issue. And over the last several years, major nations, all major nations have made a climate commitment. Net zero economy by certain date. United States is 2050, China is 2060, India is 2070, Germany 2045. This is race to the top, which is fantastic. More than 60% of the Fortune 500 companies have made a climate or sustainability commitment, regardless of the ESG vulnerabilities right now. They've made a commitment. And the United Nations has some sustainability goals, development goals. I was there at the B20 meeting, the Business 20, which is 2 weeks before the G20 meeting in New Delhi, and the top 3 issues are sustainable development, sustainability, climate change. This is the issue of our times. But no one really knows. Despite the commitments, it's like marriage. People have made a commitment, but the details have to be worked out. That's what's going on right now. So what do we need to do? Well, the national academies have been writing reports on climate change since the late 1970s. This is the most recent one of what do we need to do. The top curve, this is the vertical axis, is the emission rate. Today is about 40 or total about 50 with other gases. The top curve, yellow, is the business as usual scenario. The red curve is 2 degrees. That's the emission profile for 2 degrees. And the green, the gap on top, is the reduction in emissions that we have to do. And so that is on the order of 50 gigatons of CO2 per year. But that's not enough. That's necessary but not sufficient. You see the blue band at the top, at the bottom? That is the negative emissions. That is, we have to remove CO2 from the atmosphere and methane from the atmosphere to get to zero, to get to the 2 degrees within this century. So it's not either or. We don't have the luxury of that anymore. It's and. It's the harmony of and, not the tyranny of or. So how do we get there? But before I go there, I'm going to give you a second quiz. We're throwing gigatons like numbers. So here's the second quiz. What is the weight of all 8 billion human beings on Earth in gigatons? Now, don't have to take out your phone and calculate this anymore. The weight of all 8 billion human beings in gigatons is half a gigaton. And we're talking about dealing with tens of gigatons of CO2. And I would postulate that whatever 10 billion people consume will produce gigaton scale impact. We know about electricity, heating, and cooling. We know about transportation, which is 14% of the global emissions. Food is 25%. Textile, water, steel, cement, and information. The fastest growing sector in the electricity sector, the fastest growing element in the United States is data centers. And the more chat GPT we do, which is fantastic, it's a trick, it gives me wonderful limericks, but it consumes a lot of energy. If you step back for a moment, you realize that this is the largest transformation humanity has ever undertaken. 8 billion people going to 10, $100 trillion global economy that is growing, transforming in the next 10 to 20, 30 years. I wish I was an undergraduate student going in right now because it is so exciting as an engineer to solve some problems. Now, I'm going to focus on energy, but the same thing could be said about water, food, etc. But let me focus on energy for the time being. There's some good news. And the good news is that we have made progress. Unconventional gas has really given us energy security, given us ramping capability on the grid, and helped us move away from coal. We have renewable electricity at the terawatt-hour scale. The first time in history, carbon-free electricity at the terawatt-hour scale is the cheapest way to produce electricity today. That's amazing. Automobiles, electrification, in the next few years, when the cost of batteries reaches $100 a kilowatt hour, It'll be range and cost competitive with gasoline cars without subsidies. Every car company has an electrification plan. This is a tectonic shift after 100 years. And let's not forget LED lighting, especially for those people who did not have access to electricity and lighting, they got lighting for the first time. This is amazing, and the costs have come down dramatically. These are necessary but not sufficient to address the climate and the sustainability issue that I was talking about. We need much more. Multi-day grid-scale storage at 1/10 the cost of lithium-ion batteries. Small modular nuclear plants at half the cost of what we spend today. Refrigerants are very potent global warming greenhouse gases. Building energy efficiency, industrial heat is one of the most difficult things to decarbonize. And of course, I talked about food, which is 25% of the global emissions. And the global carbon management, as I said, is really removing the CO2 and putting it somewhere down and permanently storing. I cannot talk about all of them. I'll talk about a few. I'll start with a grid. This was called the greatest engineering achievement of the 20th century, and it is. Without that, we won't have lighting, we don't have things that we do out here today. But that grid has to change. Not been thrown away, but changed. Because it was never designed for solar and wind. We have issues related to cyber security on the grid that we did not have before. We are seeing wildfires, and people in California know what the issues are on climate change, interplay of climate change and the grid. And of course, we have loads today of hundreds of kilowatt sometimes, which are way more than, this is EV charging, that way more than what homes are, which are typically few kilowatts or so. So the grid has to change, has to be adapted. This is the current paradigm of the grid. You have large generation, turbo machinery. You have electricity flowing one way from transmission, substation, distribution to the home. And that's the paradigm. The architecture of the grid is still the same Tesla Edison architecture. The devices are new, of course, but the architecture is still the same. And the paradigm, our jurisdictional boundaries, have been created around it. The grid operators are regulated federally because they cross state boundaries in the United States. That's FERC. The utility distribution is local, is state-wise, and then we have up to the meter, and then it's consumer. In this grid now, which has been going on for 120 years or so, we're injecting more than 50% renewable. It was never designed for that. And you get all kinds of things like the duck curve. The duck curve is in the middle of the day, you have so much solar that you got to ramp down the other sources, and in the evening when the sun goes down, you got to ramp up like crazy. So this ramping capability, the flexibility, is super important right now. And then, of course, this is on the supply side. On the generation side, there's volatility we have to maintain. On the demand side, we got networked thermostats, we got EV charging, and you got solar generation injecting electricity the other way. You got volatility on both sides. And the question is, how do you manage? The future of the grid has been the communication between the generation and the load in the past has been frequency, 60 hertz, plus minus 0.035 hertz. That's the tolerance we have. We have other technologies today with much higher fidelity of information. So there needs to be, the real smart grid is that feedback loop and a synergy, not just energy, but synergy created by information technology protected against cyber. That's the future. That's what we are looking at. And now new markets are being created as well. Long duration storage, very big deal. The grid was, as I said, was never designed for fluctuating generation. The question is how much, and how much would it cost? On the x-axis out here is the penetration of renewables onto the grid. The more renewable penetration we have, the more storage in terms of duration of storage we need. So 80%, you'll need about 100 hours, about 4 or 5 days of storage somewhere, right? And if you're going to store that much and use it only a few times a year, the cost of the battery has to come down. So today we have lithium-ion battery, which at 30–40% penetration of renewables on the grid, which is what California is, you need a few hours of storage, the daily storage, and for that, lithium-ion battery is fine. But lithium-ion battery bottoms out. The CapEx, just the bill of materials, at about $60 a kilowatt hour. But below that, if you want to go deeper into penetration of renewables, you have to go lower, and you have to go lower than $10 a kilowatt hour. What technologies do we have? Well, when I was in ARPA, we actually funded a few things which are now in the pilot stage. Hopefully by the end of this decade, they'll be actually commissioned into the grid. But this is still under development. While electricity is super important, we cannot electrify everything. We need a fuel. In fact, it is dangerous, risky to electrify everything, because if something goes wrong with electricity, then we have a problem. So you need some redundancy in the system. We need a fuel, a clean fuel. Today, oil, gas, and coal provide 80% of the primary energy. And the question is, can we develop a greenhouse gas-free, energy-dense fuel at that scale? What is that scale? We have a global network of pipelines, of tankers, and things that move this energy all over. We need that scale of energy, of fuel. So there's a lot of discussion right now on hydrogen, on greenhouse gas-free hydrogen. Let me say a little bit about it. Hydrogen is very important because if you have hydrogen, you can take CO2, convert that into plastics or jet fuel or any kind of fuel. That technology exists. You could use it for steel, cement, and for heating and petrochemicals. You need hydrogen. That's used today for ammonia as well as petrochemicals. But the hydrogen has to be greenhouse gas-free, emissions-free. And it has to be low cost. The DOE has come up with a hydrogen earthshot that we had planned during the transition team, and now it has come out, is $1 a kilogram within this decade. What is missing on that one is the gigaton per year scale. Today's hydrogen consumption or production today in the world is 100 million tons, 0.1 gigatons. But if you're going to do all of these other things, we have to target a gigaton per year. Where are we today? There's a lot of excitement about electrolysis. I'm super excited about that. Electrolysis is splitting of water. Now, this is today's projections of where this would go. I won't go into the details of this, but it could get down to $1 a kilogram if you have very cheap electricity, carbon-free, 24/7, and if you have very low-cost electrolyzers, and that has to come down in cost. It's not quite there yet, which is why the Inflation Reduction Act has a $3 per kilogram subsidy to bring it down to make it competitive. Otherwise, it's about $4 or $5 a kilogram. What is important also is the scale. Today's production of 100 million tons of hydrogen, if we are going to do this purely by splitting water, it'll need 5,000 terawatt hours of greenhouse gas-free electricity. The United States today, all electricity is 4,000 terawatt hours. And the world produces today greenhouse gas-free electricity 11,000 or roughly 10,000 terawatt hours. So half of that we'll have to use for hydrogen. So if we are to do this all by splitting water, we need a few other grids to be made. So while that is absolutely worthwhile thinking about, we ought to have some other options as well. So this is traditional way of making hydrogen is from carbon as a reducing agent or methane as a reducing agent, react with water, and you get syngas, and you can process the syngas again, and you get CO2 and hydrogen. Today we let the CO2 out, and that's at $1 a kilogram, which is where the number comes from. If you capture the CO2, it's about $1.60, and there are other processes as well. So you could capture the CO2, but then you need the infrastructure of CO2 management. And I think one should also have a few other options, since this is still, the rest of it's still in the R&D stage. Can you split methane? Methane pyrolysis to produce hydrogen and solid carbon. And if you can produce solid carbon, you can put it in the back of a truck. You don't need the infrastructure. The infrastructure is already there. And one thing which is super exciting is geologic hydrogen. There are ways that nature has split water using either radiolysis or some other kind of reducing agent down in the ground to produce hydrogen, and this is super exciting. I think those options need to be explored if we are to look at hydrogen very seriously. Let me say a little bit about atmospheric greenhouse gas removal at the gigaton scale. It has to be at the gigaton scale. There are a lot of ideas being thrown around using oceans, using ocean in alkalinization, weathering, pumping the atmosphere through fans and removing the CO2, growing plants and crops. Let me just say a little bit about the chemical. This is because this has been explored for more than a decade now. Typically, these need a sorbent, something to bind the CO2. Usually, these are amines, chemical forms, and then you need some energy to throw out the CO2 in a concentrator. Whatever we do, we need energy because this is the second law of thermodynamics. If you're going to separate out a gas, you need some energy to be able to separate that out. So, but the basic process is still the same. The sorbents are different. There's a high temperature process, low temperature process. I won't go into the details, but I'll just highlight how much energy do you need? Because at the end of the day, that energy needs to be provided. Today's technology is about 2,000 kilowatt hours per ton of CO2, mostly in heat, not in electricity. Remember the number 2,000 kilowatt hours per ton. So if you're going to do a gigaton of CO2, US emissions are 5 gigatons. Let's say we remove 1 gigaton per year. That will require 2,000 terawatt hours. All the carbon-free electricity that we produce from nuclear, solar, wind, et cetera, is in the United States is 1,500 terawatt hours. Okay? So we need to figure out, can we make this more energy efficient? And of course, if you're looking at second law, the obvious question is, what is the thermodynamic limit and how far we are from that? That's the thermodynamic limit. We're 16x higher. And so at the thermodynamic limit, as some of you know, there are no kinetics. So you got to be a little bit higher. So there's a lot of R&D that is needed to get down to about 500 kilowatt hours per ton. And in addition to that, we need another source of zero carbon heat, whether it's geothermal or nuclear, at very low cost or 4,000 terawatt hour scale. Otherwise, it's going to be very hard to do this kind of removal at that scale. Or you can go agriculture. If you look at crops, crop residues, this is the waste product. Half the crop is waste. The other half is food, roughly. The crop residues annually remove 10 gigatons of CO2 per year from the atmosphere. And we don't do much with it. In many parts of the world, they're burnt to clean up the soil, clean up the ground for the next years. So a low-cost way to make char, for example, a scalable approach to convert that into inert form so that microbial degradation doesn't produce methane or CO2. Super important in this. This has to be dirt cheap because you're producing dirt. And so we have to be really, really careful about the cost in this. While there's a lot of focus on CO2, let's not forget methane. Methane today mostly is produced from cows burping, but it's also produced from the natural gas and oil infrastructure of coal bed methane, from wetlands. And if the permafrost warms up, it could produce methane as well. That methane, you can see an exponential rise as well. And today, the concentration of methane is 2 ppm. But roughly half of the global warming that has happened so far is due to methane because it starts off with a global warming potential of 120. And methane is removed by UV radiation working with ozone, and it removes the CO2, and it goes down after 100 years. The global warming potential is 28. But methane, the short-term effects of methane are super important, and we have to figure out ways to do that. And this is a topic that ought to be funded by the federal government to remove methane. And I'm so glad to see the DOE is starting to look at this now. I talked about energy, but I come back to this. These are, I should have talked, I don't have the time to talk about water, about food, and you can go on, and this is all interrelated. You cannot separate them out. And so if you separate them out and you focus only on the energy, you could have unintended consequences on the other sectors. So it's very important to look at it holistically, and as a many-body, as physicists would say, a many-body problem. So at Stanford, I'll say a little bit about what we're doing at Stanford. Over the last 5 or 6 years, we looked at that and said, can we do this as holistically as possible? And so we have, as many of you know, we have 6 schools: School of Engineering, Graduate School of Business, School of Medicine, School of Education, Humanities and Sciences, School of Law. We had a previous School of Earth, Energy, and Environment. That came to an end. And we created the Door School of Sustainability as the first school Stanford has launched in the last 75 years. And it is really to reimagine education and research and service to the community in an all-campus way. Because sustainability, or issues that I just talked about, there are many more that I could not talk about, cannot be separated into an engineering problem alone, or a business problem, or a law. They're all interrelated. So we are looking, there's lots of things I don't have time to explain, but I want to say, end with something on education. And this is, we are throwing it at our freshman class. I teach the freshman class. So we, as we all know, we are specialized in things, in climate science, in energy, water, food, biodiversity, etc. But as I said, they're all interrelated, and these are, I call, sectoral specialization. On the other hand, we have disciplinary specialization on a campus. We have science, engineering, business, law, etc. And normally, when we teach, we go on a pixel of the intersection and go deep. And it's very, very important to go deep. People need to know their math. People need to know the laws of thermodynamics or other laws and understand and be able to solve engineering problems. But then you miss out on the whole picture. You miss out on the Mona Lisa. You look at the eye or the nose or the ear, but you don't get the Mona Lisa. And we are now in the process of looking how to go sideways and vertical and sideways on certain issues. And the way we do that, we just started this, we throw the students at the most interesting problems that people are grappling with. We throw at our students, we say, President Biden wants to make our electric grid 100% carbon-free by 2035. How are we going to do that? And then we start with that. And technology, business, laws, and markets all kind of converge together. That's sustainability. That's how we are looking at sustainability. Let me end with that picture again. And I've been using an indigenous coat, which my staff decided to paint it on my wall, office wall. And it's how we look at the future. This is the quote: "We do not inherit this earth from our ancestors. We are borrowing it from our children." And that gives, at least me, a perspective of what we do in the next 10 to 20 years is going to be extremely important with the world we leave behind for children and grandchildren. And this needs to be done, in the words of Martin Luther King, with a fierce urgency of now. Thank you.
All right, let's see if my mic is on. It is, yay. Thank you so much, Arun, for all of your wonderful thoughts there, and with such clarity and with such urgency. And we do have some time now to take some questions. And so we have a microphone over there and a microphone over there. So whoever would like to come up first, we'd love to hear your questions. Yes, we'll take right here. Yes, right here.
Can you hear me?
Yes.
Fabulous presentation, as usual. We knew it would be. So a question, we had a chance to talk a little bit this morning before your talk. A lot of the challenges nationally, like Breakthrough Ventures or even at the Door School, the Sustainability Challenge, in some sense they're looking for a silver bullet. It's looking for solutions that can mitigate a gigaton, which is a lot, as you said. It's twice the weight of all the people on the planet. So I'm wondering if there's another approach that you're looking at Stanford, which is, what I'd say is go small to go big. So rather than trying to find something that will mitigate a half a gigaton, which is Breakthrough Ventures, or a gigaton, can we unleash thousands of entrepreneurs that are looking to mitigate a few million tons? And so this is something that we did in hydropower. We actually applied AI in learning in order to put the turbines at the right balance between power and efficiency. We were able to get 10% more electricity to the bottom line without even doing anything. And we produce now we mitigate between 2 and 3 million tons of CO2 equivalents a year. That's just one. So the question is, what if we could unleash a couple thousand over the next decade? Is that a viable approach? And then the second question would be,
I think let's start with that first
Okay.
question, just because we have a limited amount of time.
geotechnology. Okay.
So I think it's this idea of like, are we convening on one huge solution, or are there thousands of little solutions?
Christine, it's so good to see you. We were colleagues in the Department of Energy together in the Obama first term. Look, right now, all hands on deck. You're right that most of the work that Breakthrough Energy Ventures and others are doing is on the gigaton per year scale. I was involved in that with Breakthrough in the early days. But that's, if you think about it, is really, we're talking about, decarbonizing the industrial sector, et cetera. This is supply side. It's not the demand side. And no one has figured out really how to get the demand side. That is, how to get to people. And I think that's an open question. We were talking earlier that the way to access people is today and in the future is going to be digital. One of the areas that I have been intrigued is the digital infrastructure that has been developed in India, which is a public infrastructure, the digital ID system, as well as the payment system. It has the highest payments in the world today. We are talking to them right now, can we use that infrastructure for climate adaptation? Let's be honest. We have a risk of crossing 2 degrees to 2.5 or 3. We don't know what that world looks like. And we need to make sure that people are protected. So while decarbonization is super important and adaptation is going to be absolutely important. I was in Hong Kong a few weeks ago, and 20-25% of the rainfall fell in one day. You don't have to give attribution signs to the people out there to say this may be climate related. They have a gut feel this is different. And so protection of people, and what happened in Libya, for example. So I think we need a digital infrastructure to be able to access people and look at the demand side, which I don't think Breakthrough, and for that matter, any other group has really effectively done that. And for that, you need entrepreneurs around the world to take the digital infrastructure, adapt it to their local communities. And I think that's the way to do it.
Great question, thank you. All right, we'll take the next one over here.
My name's John Kuhn. I'm an environmental engineer in private practice, and recently, second career was teaching at Georgia Tech in the environmental engineering program. You mentioned the rapid growth of population, up to 10 billion people. Recently, I've been seeing articles about the decline of population. The number I've seen, I think, is down to 2 billion people in 300 years. That's a long time. How does that influence your thinking?
Yeah, so I think in certain parts of the world, regionally, the population is going down. I mean, China had a one-child policy. That population, there'll be more people dying than being born, and so that population. Japan is already seeing elements of that. US is fine. Europe, if immigration is not there in Europe, their population decline. I don't know if that's what you mean, but that is, so the question of, there are many implications of that. On sustainability issue, you do need people to be able to produce these things. But at the end of the day, if you're going to feed or provide shelter and water for more and more people, as long as we do it sustainably, it's fine. Otherwise, if we do it the way we have done in the 20th century, there are other challenges that we'll face.
Great. In terms of time, I think we're very close to time, but we're going to take a quick question, one last question here. And I encourage you all to take all the questions you have. And when we come back to the forum, we're going to be doing a deeper dive on this subject with our other panelists. So we will take some more questions then as well.
Thank you very much for your presentation. As you've pointed out, the climate change is mitigated by reduction of greenhouse gas concentrations in the atmosphere. And sadly, those concentrations continue to increase. And all of the research underway is excellent, but we need a plan. And so you've talked about this. The estimate is on the order of hundreds of trillions of dollars to reconfigure our global energy infrastructure. How do we develop a plan starting with existing emission points, plans for every emission point, then integrating technology, identifying technology needs so we have a market back and then research forward and connect them together? We need that plan because today we're spending lots of money, but we're not seeing the improvements reaching the world yet.
So I think it's really a combination of policy, both we have seen the Inflation Reduction Act. I think that's just a first down payment, to be honest. I'm talking only about the United States. The Inflation Reduction Act is really a bunch of carrots. There are no sticks in it. The sticks got dropped out, the first thing. And I think you need a combination of carrots and sticks in terms of policy to be able to transform the economy. I think you can get to some point with the incentives, et cetera. I think the market, you're talking about market, absolutely. If there are market mechanism, we should be following that. There are some market failures, like building energy efficiency is a market failure, and we need other kind of sensible regulatory policies for that. This is a long topic. I'm not sure we have the time for it. We can have a conversation about it later, yeah.
Yeah, but thank you for the question. And as I mentioned, there's going to be a forum later. So I know there are more questions here. We'll save those. And Arun will be back as a member of our panel later. And we'll get to dive into sustainability even more. So thank you, Arun, for just a wonderful plenary.
Thank you.